Hello, this is Dr. Christy Lukes, and this is a video lesson for Chemical Engineering 4096, an introduction to design, in particular of batch processes. We will be looking at Chapter 3 of the textbook, which again is on batch processes. What we're going to be learning in this chapter is that batch processing is very different from continuous processing. And the design equations for this are inherently unsteady state. Scheduling is going to be an important feature of this, and that there are different types of scheduling patterns. In this lesson, we're going to be looking at the first two of these, and we'll save the last two as goals for our next lecture. We're going to be going through an example in the book. I am not going to go through it slowly enough for you to really absorb everything. So stop, work through this on your own, read in the book. But basically, they go through this example and how to do these calculations. So this is for the production of an active pharmaceutical ingredient that they abbreviate API because that's a really long name. And the batch takes 7 steps. So step 1 is a mixing and heating step. There are 500 kilograms of reactant A added to 5,000 kilograms of a mixture of organic solvent that contains 60% excess of the second reactant, reactant B. And this goes into a jacketed reaction vessel. The reactor is sealed, the mixture is stirred and heated using steam on the jacket side until the temperature gets to 95 degrees C. And then they say that the density of the reacting mixture is 875 kilograms per cubic meter, and it takes 1.5 hours. Okay, that's step 1. They mix the materials and they heat them, and a reaction takes place. Step 2. Once the reaction mixture has reached 95 degrees C, a solid catalyst is added, and the reaction actually happens while the batch of reactants is stirred. The required conversion is 94%, and this will take 2 hours. So this describes how the reaction is going to happen. We want the reaction now to stop, so step 3 is that the reaction mixture is drained from the reactor, passed through a filter screen that's going to remove the catalyst and stop any further reaction. They tell us that the screen is an SC301 and that the time is going to be half an hour. Next, we have the distillation step. The reaction mixture, which at this point contains this API product, the solvent, and any of our unused reactants, is going to be transferred now to a distillation column. It's going to be distilled under vacuum. Virtually all of the unused reactants and about 50% of the solvent will be removed as overhead product in roughly 3.5 hours, and the end point for the distillation is when the solution remaining in the still contains less than 1 mole% of reactant B. This will ensure that the crystallized product produced in this step 5 meets your specifications. Next, we need to crystallize our product. The material that remains in the still is going to be pumped to a crystallizer where the mixture will be cooled under vacuum again, and about 60% of the API from step 2 will crystallize out. This should take 2 hours. Step 6 is going to be to dry our crystals. So we'll filter from the crystallizer and place these crystals in a tray dryer where any entrapped solvent will be removed, and this should take 4 hours. The dried API is sealed and packaged in a packing machine and then sent to a warehouse for shipment to the customer. And this should take about an hour to do your final packaging step. And they want you to do a preliminary design on the required equipment items for this batch process. So they go through these, each one, with great detail. We're going to not use quite so much detail. So step 1 is the mixing of the product and heating it to the point where it's ready to react. They give us molecular masses, they give us masses of each one, they give us specifications about what the purities are. How do we do this? Well, we need to figure out what the volume is. They take standard that the vessel should be about 60% full. That allows for a little bit of expansion, overfilling, if it gets hot and expands. Okay. Based on this and the density that they know, they come up with a volume of 6.286 cubic meters. Now, it is not normal to go to the trouble of having something designed that is exactly 6.286 cubic meters. That's expensive. And I misspoke. They look at this and they do the calculations. They find out the volume they actually need. You don't want a vessel that's exactly that size. You'd like it to be a little larger. So they assume that the vessel should be about 60% full. That allows for a little expansion. Next time maybe you need a little bit more material to process. So it gives you some flexibility in operations, but not too much. You're not oversizing things too much. So if you do that at 60%, they come out with 2,768 gallons. Now that's not normal to have something ordered to exactly be that size. So typically you round up to the nearest standard size. In this case, they usually go by like 500s. That would be 3,000 gallons. And then you need to check and see how much heat transfer is going to be required. We need this within 1.5 hours to reach a temperature of 95 degrees Fahrenheit. So our energy balance is shown here, the data. Now some of these are assumed values, and they make an assumption of a tank height to diameter ratio is 3:1. Now in a later chapter in the book, they give some guidance on how you might assume some of these values, but they are exactly that. They are assumed values. They are values that are typical of what you might actually see in industry. When they do this, they say the temperature can be reached in 55 minutes, which meets our needs, and that if you do that, then the tank is going to be 1.7 meters in diameter, 2.8 meters high. The next step is they're going to add the catalyst and let the reaction take place until the conversion reaches 94%, and they want the time to be 2 hours. For our reaction, we're going to use the kinetic expression. Here it's dCA dt is negative KCA CB. K is given. We would look it up. Okay. And if you solve this, then we end up with our expression here. We have 60% excess B. You can kind of fight your way through the math on your own, but integrating this expression, you end up with this expression here. Plugging in the values that we know, we end up with the time is 118 minutes. It's less than 2 hours, not a lot less, but it's less. So we're good. We've got a satisfactory design for our reactor. And next we go to step 3, where we're going to drain the mixture from the reactor, pass it through a screen filter to remove the catalyst and stop the reaction, and that will take half an hour. We're just going to model this one as a draining tank. Okay? Filtration will be slower than just simply draining the tank, but we can do the model with the draining tank and then round up. And if you assume that you're going to use a Schedule 40 pipe, and a 2-inch Schedule 40 is a pretty common value there, you can get a linear velocity, okay? And then use Bernoulli's equation, substitute that into the model for a draining tank. This is something that you should have seen in earlier courses, and integrate solving for H, and we end up with 13 minutes. You round it up to 30 minutes. Yeah, we're good, okay? So we can drain our tank. We've got a plan for that with a 2-inch Schedule 40 pipe. And then step 4, we're going to now do the distillation. Now this is batch distillation. We have 4 components. We have reactants A and B, we have the solvent, and we have our final product. They've named them A, B, S, and P for convenience. And the information is summarized here of what comes out of the reactor. Now they heat it up and then run it through. These are the variables, and if they do this using batch distillation, the equations are in the book if you want to look them up, or you can look them up from your old separations textbook. They see that this is going to take 70 minutes, so we're good. Oh, here are the equations for this, and 2.3 hours will reach our goal. If you add in preheat time, then the 3.5 hours is satisfactory. And again, these are just equations that you've done in your distillation courses. Then we're going to pump it to a crystallizer. We're going to filter the crystals and dry them, and then we're going to package them. And normally we don't need to do a lot of heavy design work for some of these things like packaging. Just need to know what volumes and call a vendor and you've got it. So for the cooling and crystallization, they just estimate it using lab experiments, and they say that the amount of product that will crystallize is 80% of the product that is recovered. 60% of the product that was produced in the reactor will be recovered, and that will take 2 hours. And then the filtration or drying, again, you would just simply go through and do lab experiments typically for this. And the same, and that should say step 7. That is a typo, step 7 there for your packaging. You just try it and see if it'll work. And yes, so you can do that in 1 hour. So this is sort of the basics of how you can do the design for batch process.